Okay, great. So good evening. Welcome back. It's nice to have you all with us at the fourth lecture in the OSMU 23 series. So it's my pleasure to welcome my good friend Niels Gresnigt to give today's talk. Niels was born in the Netherlands, where he spent his early childhood years before moving with family to New Zealand, where he did his high school and later obtained his PhD in mathematical physics from the University of Christchurch in Canterbury in the year 2009. Currently, Niels is a faculty member in the Department of Physics at the Zian Ziatong Liverpool University in Suzhou. Niels and his collaborators have made important contributions regarding the role of division algebras and sedenions in understanding the standard model. So we really look forward today to hearing from him on the Cayley-Dickson algebras, braids, and the standard model. Over to you, Niels.
Okay, thank you for that introduction to Jinder, and thank you to Michael and to Jinder for organizing this very interesting series of talks. So today, you can see from the title of my talk, I want to talk a little bit about the Cayley-Dickson algebras, braids, and how they may relate to the symmetries and the particles that we find in the standard model. So what I've tried to do for this talk is break it up in three parts. So first I want to give a little bit of a review, an overview of what's already been done. And I'll focus mostly on the work that's been done by Nicole Fury and Jeffrey Dixon, although other people have looked at similar ideas. So I want to take about 15 or 20 minutes and go over some of the main themes of their research and the main results without going into too much detail, because I'm sure they will talk about it in more detail themselves in the near future. And then later on, I want to talk about two ideas that I've been working on myself. One is related to the algebra of Sedenions, and another one is trying to relate the division algebras to a certain topological representation of fermions in terms of braids. Now, these two ideas that I've been working on, they're far from complete, so it's very much still work in progress. So I really hope to have some comments and some questions at the end, hoping to stimulate some interesting discussion. So just to motivate everything, if we look at the standard model of particle physics, then we know that that is a gauge theory based on a certain symmetry group. And that symmetry group has different factors in it for the different fundamental forces. So the strong force, the weak force, and such. And in the particle multiplets, they fall into certain irreducible representations of the gauge groups. And this raises certain questions. So we know that the standard model works really well, and we can use quantum field theory calculations to predict the outcome of experiments to a really high degree of accuracy. So certainly it works really well, but from a fundamental perspective, one might wonder where the gauge group of the standard model might come from. Does this come from some deeper underlying theory? And likewise, one might ask, why do only some of the multiplets of the Lie group correspond to particles, whereas others do not? We might also ask, well, why are there 3 generations of fermions rather than any other number of generations? And we might also ask why why the SU2 interaction is chiral, whereas the SU3 interaction is not chiral and is exact as well. So there are different ways to go about trying to answer these questions. And one common approach instead of grand unified theories, which is, well, let's take the different gauge groups and try to package them together in one larger group. So the smallest group that seems to be possible for is SU5. And some other examples are spin 10 or the Patti-Salam model based on SU4 times SU2 times SU2. And so this might answer some of the questions from the previous slide, but it also raises a lot of other questions. For example, well, why these groups? Why not any other group, for example, SU12? Right? Because there's infinitely many of them. So how do you choose? Also, or how do you break up your larger group to the standard model gauge group? And why should it break to exactly the standard model gauge group rather than some other factor of subgroups? In addition to that, a lot of the grand unified theories also predict additional interactions in particles, which we so far have not observed. And all of these models turn out to be single generation models as well. So they don't have much to say about describing 3 generations of fermions. That is something that you have to implement by hand. So you have to impose by hand. There's no underlying theoretical reason for it. So another approach, which is very interesting, and I first came across a few years ago when I came across Nicole Fury's thesis, was that people have been looking at division algebraic unification. And the approach there is to search for a fundamental mathematical framework, which is going to contain both the gauge groups as well as the leptons and the quarks that they act on. And the idea is to do that in terms of some algebraic structure that is allowed to act on itself. Well, one immediate question then is, what should that algebra be? Because we have so many different algebras we could, in theory, choose from. And particularly, if you look at the Lie algebras or Clifford algebras or Jordan algebras, there are infinitely many. However, there are only 4 norm-division algebras over the field of real numbers. So these are the real numbers, complex numbers, the quaternions, and the octonions. And so the question that Nicole Fury asks in her thesis, and Cayley-Dickson has also looked a lot at this, they ask is, well, could these algebras, since there are only 4 of them, could they serve as the algebraic source from which we could derive both the standard model symmetries and the particles in a unified framework? So I want to spend a little bit of time going through these ideas and then what the results are to date, or at least some of the results. So Cayley-Dickson, he's written a couple of books on this and a lot of papers. He studies the algebra, which is the tensor product of the 4 division algebras, and then looks at different invariant subspaces in relation to the standard model symmetries and particle multiplets. Whereas Nicole, is very similar. She studies the minimal ideals of CL4 and CL6. And as I will show later, these Clifford algebras can be derived from letting tensor products of division algebras act on themselves. So the key idea is to identify the leptons and quarks as elements of the minimal ideals of certain Clifford algebras, namely those that can be generated from the division algebras, and identify the gauge symmetries as those unitary symmetries that preserve the minimal ideals. So that's the basic idea, and then that packages both the particles and the symmetries together into a single algebraic framework. So in this talk, I'm mostly gonna follow Nicole's construction because it's the one I'm most familiar with. But it's what Cayley-Dickson does is also very similar, and other people have also looked at very similar ideas. So here are just a few papers or a few references for other people that have looked, but it's by no means exhaustive. So of course, there's lots of other people that have looked at these ideas as well. And this approach so far seems to be fairly promising. So that the number of distinct particles that you can get is dictated to you by the dimensions of the minimal ideals. And similarly, the gauge symmetries are dictated to you by those unitary symmetries that preserve the ideals. The electric charge and also hypercharge come out quantized automatically. And SU2 is automatically chiral, whereas SU3 is not chiral. And it doesn't seem to predict any additional particles or interactions that we don't observe. So we don't have any issues with, say, proton decay. Now, some limitations are that the results seem to mostly be talking about a single generation of fermions, although later I'll give a few approaches towards describing 3 generations. And also the phenomenology of these algebraic models hasn't really been studied. So for example, neutrino oscillations or quark mixing, as far as I'm aware, no one's really looked into that yet. And then of course, there's the question about dynamics. How do you implement dynamics? And I know Tajinder has done some interesting work in this regard, looking at, let's say, trace dynamics. Now, the division algebraic approach is not the only game in town. So there's other approaches that people are looking at that I'll just quickly mention here. So one is looking at exceptional Lie groups. That's quite interesting because there's only 5 of them. So again, you don't have an infinite set of algebras that you could choose from. The exceptional Jordan algebra, there's only 1 of them. So that's really interesting. And also non-commutative geometry. But I'm not going to focus on these because we don't really have that much time. So hopefully most of this is already familiar to most of you. A division algebra over a field is an algebra where division is always possible. So if the product of 2 elements is 0, it means that either A or B must be 0. Now, interestingly, nature actually only gives us 4 normed division algebras over the field of real numbers. Real numbers, complex numbers, quaternions, and octonions. And they have respective dimensions 1, 2, 4, and 8. Now, when we go from a smaller algebra to a larger algebra, at each time you lose some of the properties that the smaller algebra had. So, for example, the complex numbers are not self-conjugate, whereas the real numbers are. If you look at the quaternions, they are no longer commutative, but they're still associative. And finally, if you look at the octonions, then you find that they're non-commutative and also non-associative. So the algebraic structure seems to break down as we go to larger algebras. So a very quick review of the quaternions then. These are a generalization of the complex numbers, where now we have 3 imaginary units, Q1, Q2, and Q3, squaring to -1, and also the product of all 3 imaginary units is also equal to -1. And from that, it follows that Q1 times Q2 is equal to Q3, and that they anti-commute. The automorphism group of the quaternions is SU2. And it's worth pointing out at this point that the complexified quaternions, which we will look at soon, so the tensor product of the complex numbers and the quaternions, they are no longer a division algebra. So once you start taking tensor products of division algebras, the resulting algebraic structure in general is not going to be a division algebra. And so they end up containing non-trivial projectors. And this actually is going to be very important in what follows. Now, I mentioned earlier that one wants to look at an algebra and let it act on itself. So if we consider the algebra of quaternions and we let it act on itself, well, then we can do that action either from the left or via the right. And it turns out that for the quaternions, this actually gives a different action. So each action, if we want to, we could represent it as a 4x4 real matrix. So for the moment, I'm just talking about the real quaternions. So for example, if you act with Q1 on this vector, which is this column vector, which is the quaternion basis, then you can write that as a 4x4 matrix. And if you compare the left actions and the right actions, you will find that the matrices that you get from the left actions are distinct from those arising from the right actions. And you find that the left actions as well as the right actions, they anti-commute among themselves, but they will commute with each other. So one ends up with 2 distinct copies of the quaternions. Actually 3 copies. So the quaternions you start with, and then the quaternions that you generate from the left actions, and the quaternions that you generate from the right actions. So when we consider all the possible actions, so both the left actions, the right actions, and the 2-sided actions, then you end up with a basis for the 4x4 matrices over the real numbers. And that's known to be isomorphic to the Clifford algebra CL31 or CL22, right? The real Clifford algebras. So now if we complexify the quaternions, then each of them, the left actions and the right actions, each give us a copy of CL2, which when we tensor product them together, we get a copy of CL4. Okay, and we'll come back to this algebra in a few minutes. Before we do that, I want to look at the octonions. So the octonions are an 8-dimensional algebra, and this time we have 7 imaginary units. And their multiplication is nicely described in terms of the Fano plane. When here the notation, I've left out the E. So I've just written the subscripts here. And if you follow the arrow, it tells you what multiplications are. So each of the lines here, including the circle with 1, 2, and 3, corresponds to a quaternion subalgebra of the octonions. So in total, there are 7 of them. Now, I should mention here that the multiplication table that I'm using is actually a little bit different to the one that, for example, Cayley-Dickson or Nicole Fury use. They seem to like using a different one. So different authors seem to have their own preference. There's different multiplication tables you could choose. I quite like this one. So the octonions are not commutative and they're also non-associative. So there's an example of that there. So when we multiply general octonions, we need to be a little bit careful about what order we multiply them in. And basically, as soon as we take 3 elements of an octonion that do not lie in a quaternion subalgebra, so for example, E4, E7, and E6, if we look here, you can see that E4, E7, and E6 do not lie on a straight line here or on the circle. So they do not form a quaternion subalgebra. So their product is going to not associate, anti-associate. Now, very interestingly, the automorphism group of the octonions is the exceptional Lie group G2, which is 14-dimensional, and it contains SU3 as one of its maximal subgroups. And you can obtain that subgroup by fixing one of the imaginary units. So for me, I will choose E4, which is the one in the middle of the Fano plane here. Or equivalently, you could say that SU3 preserves a complex structure. And it's this observation that initially led to trying to connect the octonions to the quark color symmetry back in the 70s. So now let's have a look what happens when we let the octonions act on themselves, just like we did for the quaternions. Now we need to be a little bit careful because the octonions are not associative. However, if we consider the composition of actions of the algebra on itself, then we would get something that is associative by definition. So here I'm going to borrow Nicole Fury's notation and put a little arrow over any product, which just means that we're going to multiply in equation 12 here. First, we multiply the octonion X by EJ, and then we multiply by EI. So in this way, the order of multiplication is always well defined. Now, if you look at all the different combinations or all the different possible actions that you could do from the left, you find that you end up with new maps that you cannot represent just as a single octonion acting on another octonion. And so in total, you find 64 different maps, and these end up generating the complex Clifford algebra CL6, which is isomorphic to 8x8 complex matrices. So each of these adjoint actions, or each of these left actions, we could write as an 8x8 matrix. And we have 64 of them, and so we get a basis for CL6. Now, unlike for the quaternions, in this case, it actually turns out that the left actions and the right actions are isomorphic. They're the same algebra, right? So both of them give you a basis for 8x8 complex matrices. So that's all I really wanted to say about the quaternions and the octonions. So now I want to give you a little bit of an overview about how Dickson and Fury have used these results, in particular CL4 and CL6, generated in this way to construct particle multiplets and gauge symmetries. So we will start with CL6, and we'll drop the slightly awkward notation of putting arrows on everything. So we take CL6, and as a basis, we can take E1 to E6. Now, from this basis, we can define a new basis called a width basis, which we write in terms of alphas and alpha daggers. And you can see that this width basis relies on having the complex I in there. So it's not possible to do this within the real octonions. So we need to use the complex octonions to be able to define this basis. Now this basis has a couple of nice properties. So they satisfy the anti-commutation relations in equation 18. And it's also worth pointing out that each of the ladder operators, so each of the alphas or the alpha daggers, are nilpotent. So if you square them, they give you 0. And from these, it's very straightforward to construct the minimal ideals of a Clifford algebra. And the way that that works is just looking at equation 19, is by letting the algebra act on a primitive idempotent. So primitive idempotent is something that squares to itself. And in this case, that primitive idempotent will be omega times omega dagger, or omega dagger times omega, which is defined as the product of alpha 1 with alpha 2 and alpha 3, or the Hermitian conjugate of that. Now, individually, they are nilpotent, so they square to 0, but when we multiply them together, we get an idempotent. And then we can construct two 8-dimensional ideals just by letting the whole algebra act upon those primitive idempotents. So explicitly, those two ideals look something like this, where the coefficients are just complex numbers, and well, rather suggestively chosen complex numbers, but I'll explain that in a minute. And I've tried to write it here in such a way that each line has a different grade element in the Clifford algebra. So the question then is, which unitary symmetries would preserve these ideals? And so what you can find, for example, in Nicole Fury's thesis, is that those two 8-dimensional ideals are preserved by both an SU3 symmetry and a U1 symmetry. And you can generate those symmetries from these generators given here. So then one might ask, of the 8 basis states that we have in our minimal, in a given minimal ideal, how do they then transform under those SU3 and U1 symmetries? And so, for example, we find that the first ideal here, so SU, transforms as a triplet, an anti-triplet, and 2 singlets. Whereas for the U1 generator seems to give the correct electric charge. And so that justifies the labels, the complex coefficients here. So the result then seems to be that you can represent one generation of leptons and quarks with SU3 color symmetry and an electromagnetic U1 symmetry that gives you the electric charge in terms of 2 minimal ideals of Cl6, which can be generated from the complex octonions. So in this case, it's the dimension of the minimal ideal that dictates to you the number of distinct physical states that you can have. And the gauge symmetries are dictated to you by those unitary symmetries that preserve the ideals. So now let's try to redo this construction, but for Cl4. So here the construction I present here differs a little bit from Nicole's construction. So let's take a basis here, say for Cl4, let's use F instead of E, just to be different. So again, we can define a width basis, and in this case, we just have 4 ladder operators, so 2 raising operators, 2 lowering operators, and they satisfy the same anti-commutation relations. And so we can construct 2 minimal ideals in the same way. And this time we're going to construct 2 minimal right ideals. We could construct it as minimal left ideals as well. That doesn't matter. But here we're going to do it as 2 right ideals. So in this case, in equation 24, we end up with 2 4-dimensional minimal right ideals, where again, the coefficients are complex numbers. And so we ask again, which symmetries preserve these minimal ideals? And this time you find that it's preserved by an SU2 symmetry with the generators given there. And actually, you can also introduce a U1 symmetry as well, which seems to give you the hypercharge. But here, let's focus on the SU2 symmetry. And under the action of this SU2, you find that the elements of the ideal transform as 1 doublet and 2 singlets. And so again, that justifies the complex coefficients here, how we have labeled them. So the result then is that 1 generation of leptons, or equivalently quarks of a fixed color, with SU2 symmetry can be represented in terms of two minimal right ideals of CL4. And again, it's the dimensions of the minimal ideals that dictates the number of different states, and it's the unitary symmetries that tell you what the gauge symmetries are. The construction here is a little bit of a simplification from the one that you find in Nicole Furey's thesis. In that I'm just using the quaternions here, where she actually uses a slightly different, instead of using the left actions of the quaternions, she actually uses another right action, another CL2 generated from right actions of the primitive idempotence, or rather the nilpotence of the complex octonions from CL6. They're slightly different. So the other thing you can do is then to try and combine these CL6 and these CL4s together. So you could represent all the different symmetries. So the way to do that would be to consider states as belonging simultaneously to both minimal ideals of CL6 and CL4. So for example, I've written one doublet here. And so you can see that they belong to the same CL4 ideal, but they belong to different CL6 ideals. Because you can see for the CL6 ideal, it's the small omega omega dagger, and for the down quark, it's omega dagger omega. Okay, and the second equation there, that's just an example of a singlet state. And again, here, I've done this in a slightly different way to the way that Nicole has done this. And why I've done it slightly differently, I'll come back to later when I talk about braids. And so we see that the SU3 generators and the U1 generators, as well as the SU2 generators, they introduce transformations between the ideals themselves. Whereas if we want to transform an up quark into a down quark, we need to actually change the CL6 ideals. So what I've done is I've modified those SU2 generators here to include an omega or an omega dagger. So with these modified SU2 generators, if we then act on these algebraic states, everything seems to transform nicely on the SU2L and SU3 and U1. Now, since the tensor product of CL6 and CL4 is equal to CL10, it's possible to also write everything in terms of CL10. But if you were to start with CL10 and construct the minimal ideals, then you would find that you end up with a much larger set of symmetries that would preserve those ideals. You would actually end up with SU5. And that is because you'd end up with symmetry generators that mix the ladder operators from CL6 and CL4. Whereas in our construction here, that's actually avoided. And that's quite nice because it's precisely these generators that mix the alphas and the betas that give you the particle processes that we don't observe. So these are automatically excluded if you start with the division algebras. So just to very quickly summarize then, from the complex octonions, you can generate CL6, and then you can describe one generation in terms of with SU3 symmetry and electric charge. And from the complex octonions, you can get CL4, and you can do the same, and get an SU2L, and actually also a U1 symmetry. And you can combine all that together if you want in terms of minimal ideals of CL10. So that's sort of the revision part of my talk. And so this approach seems to do a really good job of describing one generation. Certainly seems very promising. But one question then would be, how do you extend this to 3 generations? So there have been a few different approaches to this. So for example, Dickson proposed taking 6 copies of his original algebra, C times H times O. So he has 2 copies of the octonions, and 2 copies of the quaternions and 3 copies of the octonions. Now, initially, to me, that looked rather strange. And I thought, well, why would you take 3 copies of the octonions rather than, say, 4 or 17? But he seems to have some reason for that based on sphere packing. But I can't say I've looked into that into much detail yet, but this choice is not completely arbitrary. So it's actually really interesting. Now, whereas Nicole, on the other hand, she actually looks for 3 generations of electrocolor states within the algebra CL6 itself. So she finds, because that algebra is 64-dimensional, and for one generation you need 16 dimensions, you actually have enough space in the algebra to represent 3 generations. And now others, right, lots of people have looked at this, so I didn't list any specific authors, have looked at the exceptional Jordan algebra, and that's the algebra of 3x3 matrices over the octonions. So that's quite interesting. So a matrix of the exceptional Jordan algebra would depend on 3 different octonions. So the idea is that each octonion would be associated with 1 generation. And also a really interesting idea that I'll come back to in a minute is Minogue and Dre. They've actually represented 3 generations, but only leptons in terms of 3 quaternion subalgebras of the octonions. So the idea I've been thinking about for a few years then is, well, what about using the larger algebra of Sedenians, which I'll define in a minute, as a basis for describing 3 generations. And the reason I thought of this approach is that each of the division algebras can be generated via what's called the Cayley-Dickson process. So you start with the algebra, the real numbers, and you apply the Cayley-Dickson process, it gives you the complex numbers, and then the quaternions, and then the octonions. And at each step, what you do is you introduce 1 new imaginary unit. And then satisfying some conditions, you can obtain the next algebra, the next Cayley-Dickson algebra. Now this process doesn't stop with the octonions, but actually continues indefinitely, generating a series of 2 to the power n dimensional algebras. Now, of course, these would not be division algebras, because the largest division algebra is the octonions. So if we take the octonions and apply the Cayley-Dickson process, you end up with a 16-dimensional algebra, which is called the Sedenians. So we introduce a new anti-commuting imaginary unit, EA, to the octonions, and then that gives us the Sedenians, where now we have 15 imaginary units, and together with the identity 1, then we have 16 dimensions. And here E1 to E7 just correspond to the original octonion units. So here's the multiplication table, which is not particularly insightful, but I thought I would share it for completeness. But one reason I like the multiplication table that I chose for the octonions is that it sits very nicely within this Sedenian multiplication table. And it's the same for the quaternions and the complex numbers. Now, in going from the octonions to the Sedenians, you lose a lot of algebraic properties. So you no longer have a division algebra, and also the algebra is not alternative anymore. So it means that even if you take 2 elements, they don't always generate an associative subalgebra. However, some other properties still hold. So since a larger algebra may be needed to represent 3 generations, one might ask if perhaps the Sedenians or the complex Sedenians might play a role. Now, one objection might be that the Sedenians are not a division algebra. But then we should remember that the tensor product of division algebras is also not division algebras. And Clifford algebras in general are also not division algebras. So I don't think that's a good reason to exclude the Sedenians. And in fact, once I started studying the Sedenians a bit more, I realized they had a few nice properties that I thought make it perhaps quite a natural candidate to try and describe 3 generations. Now, one is that if you look at the adjoint algebra, so the algebra that you generate from the left or from the right actions, like we did before, then you're going to get the complex Clifford algebra CL8, and the spin group spin 8 associated with that Clifford algebra admits a triality automorphism. And several people have considered triality in relation to 3 generations. For example, also if you look at the exceptional Jordan algebra. Another thing is if you look at the automorphisms of the Sedenians, then you find out it's really just the automorphisms of the octonions with a factor of S3. So I thought, well, that's kind of interesting. It seems that the underlying symmetries are the same as those of the octonians, but we seem to have 3 copies of it somehow. And finally, as I'll show in a minute, the algebra Sedenians contains a number of octonion subalgebras, just like the octonions contain a number of quaternion subalgebras. So I thought, if we want to represent 3 generations, could we in some systematic way find 3 octonion subalgebras within the Sedenians, and then use those 3 octonion subalgebras to represent 3 generations? Now, if you look at the adjoint algebra, so the left and the right actions of the complex Sedenians on itself, it's not immediately obvious how to generalize what happens in the case of the octonions. So each left or each right action would give you a 16 by 16 matrix. That's fine. But this time they don't satisfy the nice properties that you find for O. So if you swap the order of two of their elements, you don't necessarily pick up a minus sign. And so what you find is that if you look at all the adjoint actions, they don't close as a Clifford algebra, if you consider all of them. However, if you look at the adjoint actions of E1 to E8, we have put E8 here in green because that's the new element we introduced via the Cayley-Dickson process, then they generate the real Clifford algebra CL08. Now, another choice is actually to take E8 to E15. So if we look at all the adjoint actions of, say, E1 to E8, we can actually obtain a basis for all the 16 by 16 matrices. So now if we complexify that, we would get CL8, a complex Clifford algebra CL8. So now let's have a look at the automorphisms of Cayley-Dickson algebras. And this was actually studied a long time ago in the 60s. So if we let AN be a Cayley-Dickson algebra, where A naught is equal to the real numbers, then if theta is an automorphism of AN minus 1, or really this should be AN perhaps. Yes. So if theta is an automorphism of a Cayley-Dickson algebra, then the following 3 are going to be automorphisms of the next Cayley-Dickson algebra. So for example, if theta is an automorphism of the octonions, then theta, epsilon, and psi are going to be automorphisms of the Sedenians. But note that in general, they don't have to be equal. That doesn't have to represent
Did we lose Niels? Michael?
We appear to have lost him, yes. He did mention to me just before starting that he had a notification on his screen that his connection was unstable. I'm afraid I don't think there's anything we can do from this end except hope that he gets it back again. Yeah. Yes, it clearly we lost it. Hang on.
Oh, Niels can hear us.
You can hear us, good. But we can't hear you, unfortunately.
Niels, would you like to log out and log in again? Shall we try that?
Yeah, that's a good suggestion, Niels. I go ahead and do that. It might possibly make some difference. I just don't know, but it might make some difference if, in terms of the bandwidth available to Niels, if we were to kill our video images. Just see what happens when he tries to log on again.
Yeah, he has another 20 minutes or so to go.
Well, I'm sure we can give him additional time to finish if he gets back on.
No, sure.
Dream of cutting into his time. It's okay. I have a message from him saying that he can hear us and that he's trying to reconnect. So that's just. Niels, can you still hear us? If you just put a yes or no in the chat.
Has he reconnected?
No, not yet. I was going to suggest that he goes out completely and just, just logs in again on the OSMU 2023 Zoom site. Well, I imagine that's what he is trying to do when he says he's trying to reconnect. Yeah, but it's very strange. We had no problem at all earlier on. The link seemed fine.
Right. Not reconnected yet.
Not yet, I'm afraid, no. Unfortunately, I don't think there's anything we can do to help him from this end. It's a great pity because he was really getting into his stride. It was an extremely interesting.
Yeah, we're getting on with the Sudanians.
Fascinating presentation. Yes, exactly. It's a really fascinating presentation. Well, let's just give it a little bit more time. So let me see if I'm just wondering if it's simply not possible for Niels to reconnect, whether kind of nuclear option would be for us as the two co-hosts to end the meeting and to restart it again in the chat room. That would have, I'm afraid, mean all of the people presently in the meeting, all 24 of our participants, having to reconnect. But if it's the only way of getting Niels back, it may be worth trying.
I don't know if that would be a bit.
Well, let's see first of all if Niels can still hear us.
The worst, I wrote to him in the worst scenario, if he could kindly send me his slides, and the least I can do is.
Yes, I was going to suggest that would also, yes, if he can simply send the slides so we can at least put those in on screen.
And we go through them, and maybe at least we can all have a look at them, and then.
And we could arrange a time for him to complete the talk.
Right.
But let's just give him a little bit longer. I'm not seeing any response. Niels, if you can still hear us, can you just respond in the chat by just saying yes or no, that you can hear us?
No, I think he's. Oh, yes, he's back.
Oh, is he? Good.
Oh. As you see, he's back. Niels, can you hear us? I think he may have to be made co-host again.
Yes, okay, that's a good point. But I can only do that if I can see his if I can see him on the screen, because you.
Let's see. Again.
I can only do that if I can get his screen, and then I can click on that to make him co-host. I
So
can't do that. If
Okay.
you've got his screen, you should be able to do that.
Can you hear me?
yes,
Yeah, we can hear
yes.
you now.
Okay.
Now we can hear
Can
you.
you see me?
No.
No, but that's okay. You can start sharing your slides, please.
Yes, it says the host has disabled participant screen sharing.
Okay.
So maybe enable that. I actually changed laptop. I knew this could happen.
Oh,
so
well, I see. That's
yeah.
why.
Okay. Yeah, slide share
But
enabled.
the other one cut out and wouldn't reconnect. So I quickly grabbed my other laptop. I'll just very quickly grab the charger.
Okay,
Yeah.
but while you're doing that, we'll try to enable your co-host your new laptop. But I can only do that if I can get your, your name on the screen. Because I have to click on the three.
He's here. He's there. Michael is there. He's there.
I'm not seeing. Well, you say that, but I'm not seeing him on my screen, I'm afraid.
Let me see, because since I'm only the co-host and not the host, I cannot.
I'm not seeing anything except a screen saying that you are talking, or that I am talking. Oh, no, there you are. Okay, I've got you. Hang on, Neil. Now I can make you co-host again. Hang on.
Okay.
Wait a minute. Yes. Hang on.
Right.
Now you should be able to be co-host again.
Can you share the slides? Can you? It's possible.
Okay. Here we are. Can you see that?
Yes. They're back again.
Great to have you. Great to have you back. Take your time. Take your time.
Yeah. So all's well that ends well.
Okay. There we go. That's that. Now, where did I cut out? Hopefully not at the introduction.
No, you were on, I think, slide 27.
Okay, let's see if we can get back there. Ah, yes. Okay, so we were here. Is that about right?
I think possibly.
What was next? What was next? Yeah, we done this.
Yes.
Okay. Okay. So let me just.
Well, let's start
see.
from just before. Yeah, that's fine.
So let me just repeat a couple of points from here. Get back into the flow. So I thought three or some nice properties of the Sedenians, which I thought might make it useful for describing three generations, is that the adjoint algebra gives you CL8, whose spin 8 subgroup has a triality automorphism, which people have suggested could be a basis for three generations. And if we look at the automorphisms of the Sedenians, they're just the same as the automorphisms of the Octonians times the factor of S3. And finally, the algebra contains multiple Octonian subalgebras. So I thought if we can find, in a nice way, say 3 Octonian subalgebras of the Sedenians, then perhaps it's possible to represent 3 generations. So let me just go over this very quickly then. I'll try to speed it up a little bit so we don't go for too long. So if you look at the adjoint algebras, or the adjoint actions, so the action of the algebra via the left or the right on itself, it doesn't generalize immediately from the Octonians. And that some of the nice properties that work for Octonian adjoint actions don't help or don't work anymore for the Sedenian actions. However, if you look at all the adjoint actions of E1 to E8, or alternatively from E8 to E15, then they seem to give you a basis for the 16 by 16 matrices, and so they generate CL08. And then once you complexify, you get the complex Clifford algebra CL8. Now, the main point I wanted to make here is that the automorphisms of these Cayley-Dickson algebras were actually studied quite a long time ago already. And one finds that for the Sedenians, the automorphisms are equal to the automorphisms of the Octonians multiplied by a factor of S3. And one reason I thought the Sedenians are a good idea, but going beyond the Sedenians might not be a good idea, is that at least for the next 2 steps in the Cayley-Dickson process, the automorphisms don't give you anything new. So the only thing that happens is you pick up additional factors of S3. So I can see that there might be some benefit to having one factor of S3, but having 2 or 3 factors of S3 is probably a bit unnecessary. So I think the Sedenians provide a nice cutoff. So the question then is, well, actually a little bit more on the automorphisms. So here I've written them explicitly for the Sedenians. We have used E8, which is the new imaginary unit that you introduce to go from the octonians to the Sedenians. And one thing that you notice immediately actually is that E8 is stabilized by all of G2. Because if you remember, theta here would be a G2 automorphism, an automorphism of the octonians. So E8 is completely stabilized by all of G2. And also you notice that the original octonian units, that's E1 to E7, they just get mapped to E1 to E7 again. And same, E9 to E15 get mapped to E9 to E15 by the G2 automorphisms. So it's only the S3 automorphisms that actually mix the original octonian units with the new Sedenian units. Which is something new that emerges at this level. That this doesn't seem to happen if you look at division algebras. So what's really interesting now is that since E8 is stabilized by G2, once we choose a complex structure inside the octonians, like E4, then the SU3 subgroup of G2 is actually going to fix an entire quaternion. So we get a generalization of the result that we found for the octonion. So instead of just fixing a complex structure, we actually end up with a whole quaternion structure that is fixed by SU3. Now remember that within the octonians, you can find 7 quaternion subalgebras. Now, if you apply the Cayley-Dickson process to each of those quaternion subalgebras, you end up generating 7 octonian subalgebras of the Sedenians, which together with the original octonian algebra, which is the one in red here, gives you all of the 8 octonian subalgebras of the Sedenians. And we see straight away that all of them have E8 in them. So all the octonian subalgebras, except for the original octonians that you started with, has E8. So within the octonians, if you choose a complex structure, E4, that naturally isolates 3 of the quaternion subalgebras, namely those that contain E4. So they're the ones listed here in equation 38. And if you remember, when you construct a width basis for CL6 based on the octonians, each of the ladder operators lives inside one of these quaternion subalgebras of the octonians. So now this time, if we apply the Cayley-Dickson process to these 3 quaternion subalgebras, we end up generating 3 of the octonian subalgebras of the Sedenians, where we see they share this quaternion structure inside of them. So the idea that I've been thinking about is, well, can we use these 3 octonians here to somehow construct 3 generations? Well, then the question is how to go about doing that. So I've had a couple of ideas. The first idea was basically to apply the construction of Nicole-Fury to each of these 3 octonians. So construct a CL6 adjoint algebra and then construct the minimal ideals. So some relevant questions to consider is, well, what should the spinor space be? Should it be a complex Sedenian, or should it be 3 copies of the complex octonians, like 3 different spinor spaces? What symmetry, or how do we distinguish between the generations, and what should be the role of S3? So the first idea, which I just mentioned, was to basically generalize the idea of Minogue and Dre, where they represent 3 generations of leptons and quarks in terms of 3 quaternion subalgebras of the octonians. So can I generalize that to describe 3 generations of fermions, so both leptons and quarks, in terms of 3 octonian subalgebras of the Sedenians? So you can go ahead and just follow the same construction as before for each of these octonian subalgebras and generate a CL6 and the minimal ideals. And of course, you'd find the same gauge symmetry preserving each ideal. However, this time, because the 3 octonian subalgebras are not completely independent of one another, one of the ladder operators will actually be shared. So the 3 generations don't come out as completely independent. Also, it looks like you end up with 3 copies of SU3. So maybe that's not something you want, because I think that would mean you would have 3 generations of gluons. And I'm trying to avoid introducing any additional bosons, if at all possible. So I'm not convinced by this model. But one interesting idea that I did have with Adam, who I co-authored one paper with, was that perhaps this overlap of the 3 generations could give you a basis for the neutrino oscillations or the quark mixing. And it's really interesting that last year also Minogue, Dre, and Wilson, they suggested a similar idea in one of their papers. So this is one way to go about it. I'm not convinced that this would actually work. And in particular, it's not clear how we should then interpret the S3 automorphisms. Now, S3 can be related to triality. And also very interestingly, if you look at spin 8, you find that there's three conjugacy classes of spin 7, and S3 permutes between them. And you can pick spin 7 subgroups from each conjugacy class that their intersection is G2. So what I tried to do is I want to use S3 as a means of cycling between the 3 different generations. But one of the problems there is that the S3 automorphisms actually stabilize the octonion subalgebras. So then it's not possible to use the 3 octonion subalgebras to represent 3 generations, because S3 would stabilize it. One other idea, which I haven't looked into in detail yet at all, is to use the S3 automorphisms as a possible extension to the standard model, for example, in terms of flavor symmetry. And there's quite a few people that have looked at these ideas, these kinds of extensions of the standard model. So another model that I'm working on now is to instead try to construct 1 generation of leptons and quarks from the complex Sedenians with the SU3 symmetry, and then use the S3 automorphisms to generate 2 additional symmetries. So this way I've generalized the ladder operators that we had before from the octonions, so that each one has 4 terms. Now they still satisfy the same anti-commutation relations when they're acting as adjoint actions. And so they would generate CL6. So in that regard, you can generate or you can construct the minimal ideals, and you can build 1 generation. And then we can apply the S3 automorphism to get 2 more generations. So you can do that. So here's an example where I've done that for one of the ladder operators. However, again, you would find then that the ladder operators are not all linearly independent. So inevitably, it seems that you're going to have some overlap of the generations. But perhaps like this could be a way of incorporating the neutrino oscillations or quark mixing. But I haven't looked into that yet. On the other hand, in this construction, it seems like you would only have 1 copy of SU3 that works correctly in all 3 generations. So that's quite nice, because then you don't have to introduce 3 generations of gluons. So, but this is very much still a work in progress. So this is sort of where I'm at. Now I want to switch topics somewhat and look at something completely different that I've been working on. I worked on a few years ago, and that's on a topological representation of fermions. So I actually came across this paper by Sundance in 2006, that he wrote in 2006, before I came across all this really interesting division algebraic stuff that Nicole Fury and Jeffrey Dixon and others have been working on. And I really like this idea because it seems to give you quite an economical topological representation of a generation of fermions. And the way that this model is constructed is that you take a ribbon, so that's one of these yellow lines here, and you can twist that ribbon by either you don't twist it at all, or you twist it by plus or minus 2 pi. And so in this picture here, let's say plus 2 pi is represented by a little plus, and a minus 2 pi by a little minus. And then you combine 3 of these ribbons, these twisted ribbons together, and you connect them at the top and the bottom to a disk. And in that way, you can represent, it seems, one generation of fermions. And in this case, then the electric charge is encoded by the twisting of the ribbons. So a 2 pi twist on one of the ribbons would be a charge of a third. And the electrocolor symmetries would be encoded by the permutation of those charges. So for example, if you look at the anti-down quark, then you would see there's one plus on one of the ribbons. And so you have three choices for which ribbon you would put that plus on. So that would be the idea that would give you color. Whereas the weak symmetry or the weak quantum numbers, you would try to encode within the braiding of those three ribbons. And then the idea is that you could try to represent particle interactions, or weak interactions at least, via the composition of braids. So braids form a group, so you can compose them. So here's a picture of that. And it's speculated that the gauge bosons are possibly, they have the ribbons twisted, but they don't braid. So I started to think about how could I possibly connect this to all this really interesting division algebra stuff. I'm going to skip this. And so I started looking at what are the assumptions that go into this topological model. And there's basically three main assumptions. And that is that the twists on a ribbon, or each ribbon that's twisted, Sundance calls them helons, you can only have a twist of either 0 or plus or minus 2 pi. So there's no other twisting seems to be allowed. So you're not allowed like 4 pi twist. Also, it seems that these ribbons need to be combined in triplets and bound at the top and the bottom by a disk. And finally, no charge mixing is allowed. So for example, you're not allowed to take one ribbon that's twisted in one direction with a ribbon that's twisted in the opposite direction. So either all your ribbons are positively twisted or not twisted at all, or they're all negatively twisted or not twisted at all. So there's no mixing allowed. So these rules seem very arbitrary. So I started to think about, well, what if we try to map the basis states of the minimal ideals of these algebras that we saw before to certain braids? Could we then try to justify these assumptions? So just a very quick review then of the braid groups, that the braid group of n strands is generated by n-1 generators that satisfy these properties 40 and 41. Now, if we connect these strands in a braid to a disk at the top and the bottom, we actually end up with what's called the circular braid group. And this introduces one more generator corresponding to braiding the last string at one end with the first string at the other end. So you have these, for the case of three strings should have the relations in 42. So if we then look at the Helon model, where we look at these braids, we could basically write them in terms of capital B, which would be some braid. And then we have a vector with three integers, either 0, plus or minus 1, which would represent the twisting of each of those ribbons. Or you could write it as the twisting first and then the braid, but you have to be consistent, because if you pull this vector with the ABC through the braid, it would in general permute them, you see, so permute the AC. So you have to be a little bit careful. And now, very crucially, what's interesting is that as long as these ribbons are connected at the top and at the bottom to a disk, you can actually exchange between twisting and braiding, it turns out. So for example, here in the picture, there's an example of this where the braid generator sigma 1 is exchanged for twisting. And the way you do that is you manipulate this disk at the top. So in 3 dimensions, you manipulate that disk. And so you can always exchange all the braiding for twisting. And actually, you can go the other way as well, exchange all the twisting for braiding. So in particular, if you act with sigma 1, say, then you end up with pi twists on each of the ribbons. That's not what we want. And also, you see, it mixes there's 2 positive twists and one negative twist. So this is not what we want to get the braids that Sundance, Bilson, Thompson has. However, if you look at product of braid generators, you seem to get the characters that you want. And now if we look at the left-hand side of these that we found for the minimal ideals for CL6 over the ladder operators. Can you guys still hear me? It says my connection is unstable.
Yes,
little.
you're breaking up a bit.
Can you hear me?
Yeah, keep going, keep going.
We can hear you, but
Okay.
you are breaking up a bit.
Okay, okay. Let me just stop the video. Let's see if it maybe helps.
Yes, yes.
And so anyways, we see here that the structure is starting to look a lot like that of the minimal ideals, or CL6. So then I thought, let's map these products of braid generators. Let's associate them with the ladder operators from CL6. So take the ladder operators from CL6 and then map them to these braids in the circular braid group, and then exchange the braiding for twisting. So that's the idea between 45 and 46. And then when we do that, we actually end up with these twist structures, these on the right-hand side of these equations. And if we look at what happens to the primitive idempotents, they just turn out to give you the identity. So it doesn't do anything. So this is really interesting, because it seems then that if the triples of ribbons, they're containing the twists in opposite directions, are automatically avoided in this approach if you start with the minimal ideals of CL6, which you will recall was one of the assumptions that has to be made for the Hilo model. And likewise, the dimensions of the CL6 ideals ensures that you never end up with twisting that exceeds plus or minus 2 pi on any of the ribbons. So it naturally cuts off how much you can twist each ribbon. However, now we haven't looked at the braid structure yet. So I thought, let's try then to incorporate some braid structure via CL4. So it's the same idea here. So I've used the ladder operators, or the width bases from CL4, and I've mapped them to some braids in the braid group B3. Right, so this is actually a different braid group. Here we're using B3 and not the circular braid group. Again, you find that both the primitive idempotents map to the unbraid. And so now if we look at the different states in the CL4 ideal, we can map each of them to a particular braid. And we see that the complexity of braiding, so that is on the right-hand side of 51 to 54, so the length of the braid is not fixed anymore. Because if you look at the original Sundance's model, the Hilo model, all the braiding consists of 2 crossings. So that's no longer the case. However, if we look at the left-handed states, we find that they do have the same length and they are equivalent to their original representation. So then I try to represent the charged weak bosons. Oh, before I do that, so now we can combine the CL6 and the CL4 ideal states and map them to certain braid structures, which I do here. And so in this way we end up, so here as an example, I have a quark doublet, weak doublet, and we can map them to braids. And in this way they correspond exactly to the way that they are represented in the Hilo model for the left-handed particles. And again, you just need to be very careful when you do this about where you write the twisting and where you write the braiding, because if you pull the twist factor through the braiding, it will in general get permuted. So here's just like all the different particles. And then finally, it turns out that you can also write the bosons in terms of a braid. So I looked at what they would look like in this model. And unlike the original model, they would no longer correspond to the trivial braid, so the unbraid, where there's no crossings of the ribbons. So I get them coming out as these braids here, as the bottom of the page. Now, quite interestingly, if we now look at some weak process, for example, let's say that you have an up and a down quark that interact via a negatively charged W boson. And then you can represent that as a braid process via composition, via braid composition, which was exactly the idea in the Hilo model that the Sundance, Bilson, Thompson wanted to do. So that seems to work quite nicely. And it seems now that the interaction actually comes out as chiral as well. Because, for example, if you try to do this braid interaction on a right-handed quark, then you end up with a state with a braid that no longer corresponds to algebraically to living inside a CL4 minimal ideal. So it seems therefore that this algebraic, just like algebraically the CL4, the SU2 symmetry that you get is chiral. Once we map that to braids, that seems to carry over. So that in this braid picture, it seems you can only get the left-handed particles to interact weakly via braid composition, which is something that the original braid model didn't look at all. So basically, to summarize, I just wanted to say that what we did then was to map the ladder operators from CL6 to certain braid generators. So if we ask that the number of braid generators is the same to the number of ladder operators in the Clifford algebra, and for CL6, we actually have two choices.
Have we lost you again?
Is he just hesitating? No, I'm horribly afraid we've lost him again.
Niels?
Yeah.
Oh, you're there. Good.
I'm here.
We're not hearing you. Okay. We're almost done, yeah?
Oh, we can you hear us okay, Niels? Because we're not hearing you, unfortunately.
Is the last slide? I hear you fine. Okay, this is the last slide. So should we go over to the question answer session, the discussion now, Niels?
Well, yeah, hang on. Well, I was going to say, without Niels being able to reply, perhaps we should try and get him back first. It would be good if he could just finish the last couple of slides.
Right. Let me try to get back.
I think it would be good if we could just let him finish.
Yes.
To the Q&A. Besides, we're obviously going to need him to be able to respond in the Q&A.
Yes. He could make some change in the format. Yeah, unfortunately, the sound is not there.
Can you hear me?
Yes.
I can hear you now.
Oh man, okay. Who knows what's going on? Now, it says I'm signed out.
We can hear you, and we can see your slide, and we can see slide 54.
Yeah, but the problem is now I can't see slide 54 anymore.
You want to
hang on, let me just stop. Okay, I stopped sharing. Let me share again.
Great.
Let's see.
Yeah, perfect.
That works.
I think your slides are almost coming back.
Can you see the slides now?
Now we can.
Yes.
Just
okay, wonderful. And you can hear me okay as well?
Yes.
We can now hear.
Can you see me? Or is that pushing it?
No, we can't see you, but that's okay.
Okay. All right. Well,
this is a little bit more bandwidth.
Yes. So where was I? Where did I cut out? I was almost at the end.
You were just talking about the topological structure found in the Hilo model.
Yes, right. So basically, if we approach this from the division algebras and then the Clifford algebra CL6 and CL4, and I want to look for a braid group that has the same number of generators as the ladder operators in these Clifford algebras. So for CL6, I would have 3 braid generators together with the inverses, so that would make 6. That actually gives me 2 choices. I could choose the braid group of 4 strands, or I could choose the circular braid group of 3 strands. Now, if I look at Cl4, then I have 2 ladder operators, right, together with the conjugates. And so I need 2 braid generators. Well, that actually gives you a unique choice that it must be B3 and not the circular braid group. So if we want to combine the Cl6 and the Cl4 ideals, and we want to represent particles topologically as a single topological object, then I think that forces us to choose for Cl6 to have the circular braid group, and for Cl4, just the ordinary braid group of B3. And this could then explain why, to get the Cl6 ideals, we actually had to use all the braid generators of this slightly larger braid group, so that we could exchange all the braiding for twisting to get the electric charges and the color symmetry. Whereas for Cl4, we end up with braid structure, but we don't exchange that braid structure for twisting. So it seems very much that from this algebraic picture, you can map it down to the braid groups, and you get basically exactly the picture that Sundance proposed in 2006, which I thought is really interesting. Anyways, I think that's enough. I think it's a good idea to go to the questions before I cut out again. So thank you all very much, and apologies for the interruptions. And I'd very much like to hear your comments, your ideas, and any questions.
Yeah, thank you for a very, very interesting talk with lots of different ideas. The talk is now open to questions, please. Yes, thanks very much. And Tavian, I'll unmute you. Please unmute yourself and go ahead with your question.
And let's see if I can figure out how to get my video going. Maybe not. Anyway, so I have 2 questions, but the first one is the S3 automorphism property when you go up the Cayley-Dickson ladder. Is that essentially the same structure that, as you pointed out, we were using in that dimensional reduction paper over the quaternions?
Yes, although I'm not sure. Are you using S3? I don't think you explicitly state that, do you?
No, absolutely not. I don't know that I had even realized that that's what the symmetry was.
But you see, actually, that's a really interesting comment, because let me just go back. Can you still see the slides?
Yes.
Yeah. So actually, if you look at, where did I have these automorphisms? Yes, you see, in general, you would have these automorphisms being a subset of all the automorphisms. So if you start with the octonions, that means that within the octonions, you should be able to get, from the automorphisms, you should be able to find SU2 times S3. That would give you a subset of all the automorphisms. So perhaps that is what you have in
I am assuming from the slide that is what we had. Yes,
I think so. I think that is what you have, because the SU3 would be your quaternions, and then you have the S3 that is.
Yes.
Actually, I'm not sure. Because does that S3 that you would get, would it actually permute between the different quaternion subalgebras or not?
I think it would have to. But you have set me a calculation to do, and I was hoping you knew the answer.
No, but it definitely would be a calculation worth doing.
Okay, hey, let me slip in a second question that is probably easier. I'm not sure what you mean by a chiral SU3.
No, not chiral. I mean,
non-chiral, but I don't know what about it makes it non-chiral as opposed to chiral. I know what chiral SU2 is.
Oh, well, no, I just mean with SU, the SU3 interaction doesn't seem to care whether a particle's left-handed or right-handed.
So it's not a binary label.
No, it's not a binary label, right?
Fine, thank you. I'm happy. Thank you very much. Beautiful
Yeah,
talk.
thank you.
Thank you, Tavian. Cole, go ahead, please.
I would agree on that. That was a really nice talk, Niels. There's a lot of really
Thank
nice
you.
original ideas in here. One question that came up that I was wondering was that you mentioned that the multiplication algebra on the Sedenions is not a Clifford algebra. And so I was curious to know if you happen to know, presumably it does form some sort of an algebra. Would you happen to know what it is?
Actually, when I said that, it just occurred to me, I think it is a Clifford algebra. The thing is, if you look at all the different maps that you can generate from the Sedenions acting on itself, what happens is that you cover the CL8 algebra many times over. So there's a lot of redundancy there in the maps. Because at the end of the day, actually,
yeah, because let's see, because the CL8 is the 16 by 16 real matrices, and the Sedenions are 16.
yes.
So that should, yeah. So I guess
Yes.
okay. So
I have
maybe
spent many hours with my PhD students confused about this, and every few weeks I get it clear on my mind, and then a week later I'm confused again.
Yeah, I wonder if it's something like so I wonder if maybe it does produce CL8, but then you know how with the octonions there's the E7 is kind of redundant in the sense that you can write it down as E1 to E6. So maybe that just happens multiple times with the Sedenions.
We checked this. No, that doesn't happen. So for example,
I see. Okay. Actually, because there's only one extra okay. No, there would have to be a redundancy because there's 15 imaginary units, right?
Yes.
Yeah.
So what happens if you look at equation 31? This is not true. It actually, of course, it still works on the original octonion units, right? Like E1 to E7, it works fine.
Right. Okay.
But on the other ones, it doesn't. You end up with a plus sign.
Okay, but there might. All I'm saying is that there might be some other redundant, like.
Yes, there is. So, for example, if you look at E1 to E14, that ends up being the same as just doing E15.
Right. Yeah. So I suspect
you get a new identity, but the other ones, I haven't been able to narrow down exactly sort of which chains of actions could be shortened. So for example, in your work, right, you basically say, because of this identity, you only have to look at chains that are at most 3 in length.
Exactly. Yeah.
Yes, exactly. So I haven't been able to do that exactly yet for the Sedenions. But I think it should be possible to have a maximum chain length of 4. I think should be possible, but I haven't been able to prove that.
Okay, that that sounds I'd be really curious to see kind of how that works. That sounds really interesting.
So basically, whenever you act with some chain, it seems to behave nicely on about half of the Sedenion algebra, and it doesn't behave nicely on the other half. So if you make any chain out of just octonion elements, that would act fine on other octonion elements, but then it doesn't act nicely on the Sedenion elements, and vice versa. So you have to be a little bit careful with what the structure of it is. But if you look, for example, at, I don't know if you're familiar with that textbook by Lomas and Powell and Sorgap.
No.
They write all the adjoint actions. I think for all the Cayley-Dickson algebras, you can write them as 2 by 2 matrices of the adjoint actions of the previous Cayley-Dickson algebra.
Okay, so do you mean like the multiplication algebras, like the chain algebra, the multiplication algebra, you can write as like a 2 by 2 matrix of the previous?
Yes.
One.
Yes.
Okay.
Yeah.
Huh. Isn't that
if you're not familiar with their textbook, let me know, and I can share it with you so you can take a look. It's really interesting.
I would love that. Thank you.
And actually, one more comment, because you asked if the chains don't close as a Clifford algebra, what kind of algebra might they close as? I've thought about that a little bit. I don't
Yeah.
know. What is also interesting is that if you look at Dickson's work, once he starts looking at, I think, either t squared or t6, he makes the same claim as well, that his algebra doesn't close as a Clifford algebra. In his case, his algebra is not even a power of 2 dimensional, so it can be a Clifford algebra.
Right, and it's and it will be non-associative, so it won't be Clifford algebra. But in your case, it sounds like it might give CL8, right?
Yes, I'm pretty sure you get CL8.
Yeah.
I mean, we've checked this on Maple and Mathematica. It gets really tedious to do it by hand.
Yes. Yeah.
So
Well,
with
it's just
Mathematica and Maple, we've checked that if you look at E1 to E8, then all those identities 31 to 33 work fine, and so you can get a Clifford algebra and you get a nice basis for CL8. So that seems to work okay.
Okay. That seems like it makes sense. I've got more questions, but I think I'll let somebody else go, and I'll kind of get my thoughts sorted. So anyway, thanks again for such a great
Can I
talk.
jump in with a quick comment on this last question?
Yeah, please go ahead.
So this idea of using 2x2 matrices to go from division algebras to Clifford algebras is very much at the core of a paper that John Huerta and I and Joshua Kincaid wrote a few years ago. It doesn't cover the Sedanian case or the tensor product case, but my guess is implicit in that is a prediction that your calculation is correct.
Ah, right. Okay.
Okay, more questions.
That's good to know.
More questions, please. So in the meanwhile, Niels, could I ask you, suppose we say that we want chiral fermions, one CL6 for left-handed fermions, another CL6 for right-handed fermions. What's a good way, you think, to go about it?
From CL6?
No, or more generally, I want to pay attention to chiralities. Well, I want one generation of left-handed fermions and right-handed fermions described distinctly. I have some ideas, but I want to know what you think.
So how is that different to what you would do with, say, CL4? Like, what is the difference? The
CL4 probably tell me that SU2 acts only on the left-handed fermions, but the right-handed fermions are there in the standard model, and they take part, let's say, in the strong interaction.
Yes.
Would I make a separate CL6? When you make your CL6, you don't specify chirality, right?
No, because that's contained in the CL4. So if you look here, the way that I've written the doublet and the singlet, that contains all the information.
Where are the right-hand?
Okay. So if you look at equation 25, I've written one doublet there, right, with an up quark and a down quark. So the bits on the right-hand side there, so they're the alphas and the alpha daggers, they contain all the information about the color and the electric charge. Whereas all the bits on the left-hand side, and then the bits on the right-hand side tell you that is a doublet, and so it's going to be left-handed. Whereas if you look at the singlet states, if you look at the right-handed up quark, again, it's the left-hand side in the last brackets tells you the electric charge and the color, whereas the bit on the right-hand side, which in this case is just 1, it tells you that it's going to be a singlet with respect to SU2. So I don't think you need to introduce an additional CL6. I think one copy of CL6 is actually enough. One copy of CL6 and one copy of CL4. At least
so
for one
in what I was looking at, we looked at CL7, which is the algebra related to split bioctonions. uh,
Yeah.
which can be written as a sum of two copies of CL6,
Yeah.
interpreted as left-handed chiral fermions and right-handed chiral fermions. So now I'm curious, how is that different from what you are doing?
Your CL7, I'm trying to remember, is that complex or real?
It's a complex split bioctonion. So it's a complex CL7.
Yes, I remember. I have looked at your paper on that, and the way that you write it actually looks very similar to like the Cayley-Dickson construction, doesn't it?
Yes, yes.
Because you
So-
write for, I think for the octonions, don't you write like H and then plus omega
Yeah,
H or something?
Yeah, so there's this subtle difference between the sedenions and the split bioctonions.
Yes.
I mean, they have the split complex number coming in. Otherwise,
Yes.
apart from that, they would probably be quite similar to each other. They're both 16-dimensional, but
Yeah,
the split complex number is doing something important. I think it flips parity in a rather natural way. So I'm trying to understand what you did with CL6 and CL4. How is this different from what we are doing with CL7?
I'd have to look at your paper again more carefully, because off the top of my head I cannot remember. I do remember reading it and thinking how the way that you've written things is very similar to the Cayley-Dickson process. So it did cross my mind that it would be interesting to try and reproduce these ideas about Sedenians, but using the split by octonions, if I've got that right.
Very much so. Very much so. Yes, yes. I would be.
But I don't know that do you build any kind of projectors then from your how do you build your projectors?
Can you say that in some other way? I mean, what's the question?
So how do you, for example, project onto left-handed or right-handed particles, or how do you end up representing your particles?
The CL7 is a sum of two copies of CL6.
Ah, yes.
One of which is the parity reverse of the other. So they naturally, so if you make the first CL6 using the the left-handed neutrino, and you make the second CL6 now by extending the standard model and bringing in 3 generations of sterile right-handed neutrinos. That's very crucial. And then the excitations of the sterile neutrino give you the right-handed chiral fermions. Excitations of the left-handed neutrino give you a left-handed fermions. Is that what you are asking?
Yes, that's exactly what I was asking. I was trying to understand your construction, and in particular, how do you use the split complex number that you have?
Yeah, the split complex number is very important. That will tell you that these are parity reverses of the left-handed fermions. By introducing the split complex number omega, you get parity reversal.
Oh, maybe we could talk more about this at some stage and see. Look, if we apply this approach that you've used and you look at the split by octonions, what would happen? How would it compare to what I have?
Yes. That's
presumably you would get something quite similar.
Yeah, that was my question. Yes. Yeah. So
actually, within the Cayley-Dickson process, you don't need to end up with Sedenians, because at each step of the process, you have a choice of sign somewhere. So that's how if you have split complex numbers, you can also generate them from the Cayley-Dickson process.
Okay. I didn't know that. Yes. Yeah.
You don't have to go to the complex numbers. The other choice is to look at the the split complex numbers.
Oh,
and it's
okay,
the same
okay.
if you then apply it again to the quaternion. So at each step, you actually have a choice where you introduce a plus or a minus sign.
So what we find is that the two complex Clifford algebras, CL3 and CL7, are very special because they each have two irreducible representations, what I think called the pinner representations. And one of them is good for, chiral leptons, the other one for chiral leptons and quarks.
Yes. So I've thought about that a little bit because that's why you settle on CL3 and CL7, and you say they have this nice property, right? If you were to go to Sedenians, like I end up in CL8, if you did it your way, I think you would end up in CL9. You wouldn't have.
Yes, it does that. So yes.
Then you wouldn't, but I think once you include the quaternions, you would. Because then you could go to CL11, and a CL11 would have that nice property. Because it repeats every 4.
Oh, yes.
So CL11, you could do the same construction that you have, and then you'd have a generalization. I mean, I haven't worked it out. It's just an idea I have, but you could try to do that. If you say, take the Sedenians, and then you put in the quaternions and get a CL11, and then apply your construction. What can you describe?
Okay. So please, more questions, if anybody has more questions. So I want to open up a topic because now in this lecture series, we are getting into the thick of octonions in the standard model, and hopefully gravitation also. And many of the experts on the subject are present here. So I would like to ask everybody, to start with you, Niels, what are your big picture goals? I mean, would you like to include gravitation? Or, what are you seeking? What are you seeking in your research program?
Enjoyment.
No. What questions are you trying to answer?
Well, fundamentally, I would like to understand what is matter and why does it behave the way it does. So that's why I was immediately really drawn to the idea of representing the fermions in terms of braids when I first came across it. I thought, hey, that's an interesting idea. And it's actually a very old idea, right? To represent the fundamental particles as some kind of topological object that goes all the way back to Kelvin. Kelvin, for example, he tried to look at, could you represent particles or atoms at the time as knots in the ether. That was the idea, and out of that came the whole field of knot theory. It was then Tate that started to tabulate all the different kinds of knots, and then of course they disproved that, or they said that there is no ether. So all of that fell by the wayside. But I think the underlying idea is still very, very much interesting, because now we know that space-time is very dynamical, and we don't know what space-time looks like at a very, very small scale. Is it still going to be a smooth manifold, or does that break down at some stage? So one of the reasons I really liked the braid stuff was that you can embed them into spin networks, for example. I skipped over the slide because I didn't want to go too long. But if you look at the slide here, these kind of helons, so people looked at this, and you can embed them into spin networks, which, for example, I use in loop quantum gravity or certain background independent approaches to quantum gravity. So I've been working on that a little bit as well, because one problem then is that to get the dynamics to work is not obvious, because the normal Packner-Moos that you would apply to your graph, they preserve the braids. So you don't get any interactions.
Yeah, Niels, so sorry to interrupt you. We have a question. Sadik,
okay.
Please go ahead, Sadik.
Dr. Gresnigt, can you hear me?
Yes, I can hear you.
Sorry, beforehand, I apologize if my question is not completely true or related. And as I am a student, I just want to ask a general question I hope that is related to your subject. Actually, in the two previous sessions, in the question answer section of Professor Hille, Professor Penrose claimed that in the upper dimensions, more than 4 dimensions, the laws of physics will collapse and will change. I don't know if my question is true or not, but I want to know that in your opinion, in Actinian and in structures with more than 4 dimensions, will the fundamental particle amount change? Does it mean that we need to add or subtract new particles, or their shapes will change in twisted form or another thing in order to satisfy our theories? Thank you.
Can you still hear me? Because I just got a warning saying my connection is not so stable.
Yeah, we can
you.
still hear you.
Okay. I don't really know, to be honest. One of my motivations in all of these, both the topological and the algebraic approaches, is that I don't really want to predict lots of extra particles. I don't want a theory that makes the existing theory that works quite well more complicated. Like the standard model seems to work relatively well, so I don't like having to introduce additional gauge bosons or extra particles just to then have to try and explain them away to say, why don't I see them in an experiment? I don't think that's a very elegant approach. So I think these algebraic approaches and the topological approaches, that's what I'm drawn to, because I think they're quite elegant. But to answer your question in detail, I really don't know.
Yes, yeah. Thank you very much, Doctor.
Okay, yeah, Cole, go ahead, please.
Okay. So it's actually a question for Niels and also for anybody else who might want to speak up about it. One of the things, the 3-generation problem is a really hard problem. And it's very difficult in our models to be able to come up with 3 generations that are linearly independent. And I would say even for the majority of 3-generation models out there, most of them have been coming out with some linear dependence between the 3 generations. And I'm curious, so what I'm curious to know is if anybody, Niels or anybody else has thought about, like, is there a way to, for it to work, where the generations are linearly independent and you still end up with 3 different mass eigenstates? Do you have any ideas for how that could still work without needing them to be linearly independent?
That is the big question, and the short and the long answer is I don't know.
Yeah,
that's what I'm starting to think about now, because I think that doing things the way I've done them with the Sardinians, I don't think there's any way to avoid it, that the 3 generations are somehow going to overlap. Yeah. I'm just pleased to see in the literature that other people have come across the same problem, so that I'm not the only one. So I don't abandon my crazy ideas just yet.
Yeah, I think I would say even more often than not. I think more often than not, that's the way it's coming out. And I'd be really curious to know if there is, maybe there is some way for it to work that is, maybe there's some creative idea out there where it can work this way, and maybe it would, maybe you would get CKM matrix values out of it.
Yeah, I mean, I think that is definitely worth investigating, whether you can use this overlap in some useful way to describe more of the standard model, right?
Yeah.
I think that's the whole idea. You want to do as much as possible with starting from as little as possible.
Right. Yeah.
And I think that if this is the structure that comes out, then yeah, you have to find a way to explain that.
Yeah. Well, I think it would be really nice if somehow this.
Yeah, could I ask you at this stage, what is the problem in using the exceptional Jordan algebra to describe 3 generations?
Who are you asking? Me?
You, yes.
Oh, so I wasn't saying there was necessarily anything wrong with it, but but I was saying just in 3-generation models in general, most often what's coming out is that the 3 generations are not linearly independent. And
Yeah,
so
that I would agree with. I think I would agree
Yeah.
with you on that. Yes.
yeah, so my question is just if people have good ideas out there for how you can still get 3 different mass eigenstates while having that a property of the model, because
Yeah,
a
what
lot of
is
models
real-
with this is coming up, so it would be nice if there was a way
Yeah.
for it to work.
what it seems to me is what I saw is that the 3 mass eigenstates are not necessarily independent. You fix 2 and it will impact on the 3rd one.
Okay, and you can get 3 different values.
Yes, right. So you can get 3 different masses for like say the electron, the muon, and the tau lepton. There's something very subtle going on. It's not as simple as if I know 2 masses, I know the 3rd one. It's crazy. I don't know. It's like 3 copies of J28 make a J38. So you see what I'm saying? If you take the 3 by 3 matrix of J38, you can make 1, 2, 2, 3, and 1, 3. You can make 3 2 by 2 matrices, each sort of for 1 generation. But clearly they are not all independent. If I put 3 J28s and 1 J38, the triality somehow relates them. I mean, that's roughly what I want to say.
Okay. On a related note, the other.
Can I make 2 quick comments?
Yeah, please.
I tried to raise my hand, but I don't seem to be able to raise my hand. No, I can raise my hand like this. One is Alessio recently wrote a paper, something about 6-dimensional space-time, reducing that down to 4-dimensional space-time. And he said that if I remember our conversation correctly, he mentioned something like in 6 dimensions, the 3 generations end up overlapping, but then once you dimensionally reduce to 4 dimensions, they no longer overlap. Something to that effect. I haven't looked at the paper in detail, and that might not be exactly how he phrased it.
Okay.
But he has a recent paper where he mentioned something about this.
Yeah, I also seem to think that 6-dimensional space-time is important, more important perhaps than 10. And this is related also to SL2H being equal to SO15. And somehow these 6-dimensional space-time seems to take in general relativity and the weak force as space-time symmetries of this 6D space-time, which in turn is related to CL3 being a sum of 2 copies of CL2.
That's also a really interesting comment, because I've been thinking about whether it has been possible to generalize the construction of space-time over the division algebras to a space-time over the Sedenians.
Okay.
Perhaps Devian has any ideas.
Yeah, so I think
in a really nice book,
I'd like to
good
turn
job of
the
explaining
question
it
back at
clearly.
her and ask her to comment briefly why it's desirable or possibly necessary for the 3 generations to be independent.
Yeah, that's a good question. Cole, for you.
She's now muted herself. You may need to unmute her.
Okay, where do I find her? 1 minute, yes. 1 minute, yeah. I don't, yes, I have to. Yeah, Cole, please unmute yourself and answer. Tavian has a question for you.
Oh, I just naively, I would have expected that there's going to be like mass eigenstates.
I agree. That's, but I would like to come back to the word naive that you mentioned. Not that
Yeah.
I'm claiming that that's a naive point of view. It may
Yeah.
well be the correct answer, but it could also be that some subtle
This is
dependence present.
right. So this is exactly what I'm asking. So this was exactly my question, is that what, like, are there other ideas out there apart from the, naively expecting 3 linearly independent generations? Is there a way for us to have linear dependent generations that then still
Yeah. Cool. Could I ask you a question in mathematics, which probably you know better? When I say there are 3 copies of J28 in J38, they are related in some way to each other. Can you put that mathematically? Do you know how that works?
Well, so I think I know there's kind of, I think I know which 3 embeddings you're talking about, but this is also kind of related to another question that I was curious about. And again, this is, it's just asking if people have any ideas, any creative ideas for how to address it. Is that there's an S3 symmetry, or there's a triality symmetry, and this is a way that many people have suggested for us to be able to describe 3 generations, is that there's going to be some triality symmetry. And so another question that comes up is how do you break that, in the sense of how do you going to get 3 different masses for the 3 different generations? If the triality is some sort of a symmetry, then it's kind of also somehow got to be broken.
No, it's like if 2 of them could determine the 3rd one, they could be unequal, all 3, and yet be related in some way, which is not obvious until you finally write down the mass ratios.
Yeah, I guess in triality, I guess somehow like you would expect, like you can put 2 together to get to like the spinors together to give a vector. So,
Yeah, right. Yes, I agree.
To address Tejindra's question about the J2 and J3 O's, and simply comment that on the one hand, yes, of course, the 2x2 Jordan algebras sitting inside the exceptional Jordan algebra overlap, but equally, of course, the 3x3 Jordan matrices admit 3 independent eigenvalues.
Absolutely, I agree. That's a very good point. Yes, that I agree. Yes.
If I could make one more comment about Cole's earlier question, maybe one way possibly to have the generations independent is, if you look at the slide here, the way I've defined the ladder operators, I haven't used any of the shared quaternion elements. So I haven't used E4, E8, or E12. So there's an extra quaternion still sitting there that unused. So I don't know if that could be used.
Okay. But it would have to live. So the Sedenions is a 16-dimensional algebra. So it would have to, the 3 generations would have to live. Would they live in the multiplication algebra then, or is that?
I'm not sure. All I'm saying is, like, one other thing I could think of where there possibly might be some more space in the algebra is that the whole adjoint algebra would be CL8. And here I'm essentially taking a CL6.
Yes,
because I've taken one of the quaternions out, the E4, E8, and E12. So I could still use that quaternion, and I'd have another CL2.
Yes, yeah. So in fact, so this is actually something I've been working on for a while now. Is it's not related to the Sedenions, but it's the left multiplication algebra of RCHO, and that gives a CL8, but with a different division algebraic structure. And so I think that's what you're talking about. Then there is definitely room in there for 3 generations, and they would be linearly independent.
Yeah, so I think that's where I could see potentially where there would still be room, because here I'm not using up all the algebra, so there's still some bits of the algebra that remain unused. Yes, but then I thought that since that quaternion is shared by all the octonion subalgebras. I thought it'd be nicer, because initially I was trying to use 3 octonions for 3 generations. So I thought if they share a quaternion, perhaps it's nicer to use that quaternion for say the Lorentz symmetries that you probably want to be shared between the 3 generations, or some other symmetry that would be generation independent. But I just haven't got that far in my thinking yet, so I don't know.
Fair enough. Yeah, I think I think we'll have more to talk about after I give my talk, because it's I think some of it will be related to the things that you've been thinking about.
Great.
Yeah.
So more questions, comments, please. Could I bring in the topic of gravitation? Niels and others, anyone else who wants to address it can give their thoughts. We have the standard model. We have octonions and sedenions. We seem to have everything that we could want algebraically. Where is gravitation?
I guess
Yeah.
it depends on everybody else's model, but everybody else's model is going to be different. In the model that I've been working on now, it looks like it's very early days, but it looks like there might be a way of interpreting it as a generalization of a Vielbein. So I'm hoping to be able to bring it in some way, but it's still, for me, it's still pretty early.
Okay, thank you. And again, a general question. Niels, you said that, you want to use, let's say, the division algebras and the Cayley-Dickson construction to understand matter. Would that, from your point of view, include being able to derive fundamental constants of the standard model, like the fine structure constant?
I really haven't thought that far ahead. I'm not at all a fan of going to bigger Cayley-Dickson algebras. I think perhaps there's justification in going one step beyond the octonions. I mean, why not live on the edge? But I wouldn't really go too far beyond that, because if you look at the automorphisms, it seems you're just going to get extra factors of S3. So I don't think fundamentally you're not going to get much different. And also it's known that all the derivation algebras for all the Cayley-Dickson algebras beyond, for the octonions and beyond, they're all G2. So the derivation algebras are not going to change. So I think fundamentally the symmetries or the gauge symmetries are going to be those that you get from G2.
Okay. Tavian, could I please ask you, since you're here, you're probably one of the first ones to study the eigenvalue problem for the exceptional Jordan algebra, you and Corinne. Historically, what motivated you to do that? And do you think there's something important about the characteristic equation of the algebra?
Well, so those are 2 questions. From the point of view of the work that Corinne and I did with Rob Wilson, published last year, Niels pointed out that at the time we were interpreting our work as describing 3 generations of leptons. I would say at the moment we would be more inclined to describe it as 3 generations of quarks, because of the way that E6 with the exceptional Jordan algebras sit inside E8 with a color symmetry. What the role of the actual eigenvalues would be is something we do not have an answer for.
And
go ahead.
Yeah, I mean, if you look back at the 1934 paper of Jordan, Wigner, and von Neumann, they actually make a remark that if we expect to see any new physics different from conventional quantum theory in the Jordan algebraic formulation, it would have to come only from J38. I found that very striking, and they knew, but we have not yet been able to answer what is happening with J38 in terms of real physics, you know?
Well, from the
And-
point of view of quantum mechanics, what that